Sorry about that. So the three main branches of machine learning is supervised learning, unsupervised learning, and reinforcement learning. So what we covered so far have mainly been supervised learning. We haven't really covered unsupervised learning, but if you do want me to just tell you what that is, it's basically supervised learning, but with the input data as what you're using as a label. It's a bit weird. I didn't go into that too in depth, but yeah. And today we're going to be going to reinforcement learning, which is one of the major parts of machine learning. So to kind of motivate the differences between what we've covered, which is mostly supervised learning and reinforcement learning, I'll just get like someone to answer a simple question. So when you learn something, how do you learn it? And by that I mean, like, let's say you're trying to learn a sport or something that requires you to do things, I guess. So how would you do it? Like, just get a hand.
Like practice or repetition.
Yes, exactly. So what you do is you do a bunch of trials and errors and you learn from those experiences, right? So that's basically what reinforcement learning is, where you do actions in an environment and then you correct yourself, basically. And in supervised learning, what we saw mostly was we tell them, we know what the model should do, and then we just make the model predict what we think it should do. So this is a bit different than that, where we basically have to teach the model, like, it learns by itself through experience, and we basically tell it when it's doing something good, which is kind of similar, but it's a bit different. And that's where some of the overlap can show up. So there's like an overlap. All right. So I don't know if you have any questions about that so far, like maybe just what reinforcement learning is, but I'm going to go into that right here too. So, it got cut off. But the method of reinforcement learning basically just learns from trial and error, where supervised learning learns from labeled data and unsupervised learns from unlabeled data. So those are like the three main branches, and that's like their different meanings, I guess. I have a picture of a baby because they're like the eternal trial and error for humans. All right, so I got this picture of this dude missing a bunch to kind of give a description of him doing his trial and error, although he's kind of getting worse every time he shoots. So I don't know what he's learning, but yeah, that's like an example of trial and error, where you keep on trying something and you see like 100 different ways of failing, but if you improve yourself every step of the way, you're gonna get to your task a bit sooner. So there's two main things happening here. One is there's a person and there's the environment, right? So I guess to describe this, I would ask a question. So like, what do you think is like doing most of like the change in the environment right here? It's pretty simple. It's nothing complicated. So, yeah, exactly, the person. And what we describe as the environment here. Yeah, basically. So like the balls, the hoop, the container, the floor, that's all the environment. And sometimes even the person itself is the environment too, which is where things get a bit complicated. So to kind of show you that part, hello, is the boundary between the agent and environment. So just to reconnect what the environment and the agent are, the environment is basically everything that is not the agent. So in this example, we have like a robotic arm trying to grab some stuff out of its little pallet. And even the robotic arm itself is considered a part of the environment. And the actual part of the agent is just the code. Because the agent is just the thing that makes the decisions. So everything outside of the agent making, the decision maker, is considered the environment. And so an example of this distinction is, let's say you're an agent, you make the decisions. So what if your robot arm doesn't perform well? Or like it performs like something that we wouldn't expect? That is still something that the agent needs to take into account. So that's like kind of a example of where the reasoning why there's like a big distinction. Any questions about the distinction between the environment and the agent? Okay, so for the dude who came in late, we're just trying to go over reinforcement learning, and we just started off, so you haven't really missed much. You just have an agent that makes decisions in the environment where the decision's being made.
Sweet.
Cool. All right, so this is basically the eternal diagram of reinforcement learning. Before we had one for machine learning, which was, you had your labels and stuff. This is basically the one for reinforcement learning. So you got two main things here. One is the environment, one is the agent. We kind of went through what the two different things are. The environment is everything that doesn't make the decisions. So the part of the code that actually makes the decision, that's the agent. And the environment is everything else. So to break down this picture, we got a couple of moving parts. First thing is we have a state, and that's within the environment. So what a state is before I go about explaining everything, the reason why I'm explaining this is because to actually solve reinforcement learning problems, you have to kind of understand the different parts of it. So before we had different architectures, data, and like improvements. So that's why I'm explaining these different parts right now. Okay, so we got our little state over here. What it is pretty simple. It's just a description of the environment. And I'll show you on the next slide to make it a bit more clear. And what happens is, like, let's say I'm currently in my state right now, I'm just standing here. So I transition to this new state where I'm a bit forward. And that's what's happening over here. We're transitioning between states. And that occurs when the agent, me in this scenario, makes an action. So I made an action, I moved forward, I'm in this new state, right? So, and then the next part is the agent gets an observation and a reward. So the main thing here is the reward, and that is how we kind of guide the agent to do what we want it to do. And the second big part here is the observation. So as you can see here, the environment has state, and here the agent only gets an observation. So there is a difference there. I'll go into that a bit later, but just to kind of make the example a bit clearer here in the process, I am the agent, and this area is the environment. Let's say I wanted to pick up that chair and move it somewhere else. So I am the agent, I make an action. Oh, now I'm in this new state, which is one step forward. I make another action, I'm in a new state. I get a new observation, and I see that's closer to the chair. And I'm like rewarding myself because like I'm getting closer to my goal. And I just keep on going. And oh no, I fell down. That's a negative reward because I got hurt. So that's kind of an example of like the whole interaction. It's just a way to describe the whole like loop. And what happens, I missed one part here, and that is the agent improves. So this is a key part of reinforcement learning. It has this whole interaction loop, but if the agent doesn't improve, it's just gonna keep on doing random stuff without knowing what to do. So what happens is, whenever an agent gets a reward, like let's say they fall down, they need to learn somehow that falling down is a bad thing. So next time, they're less likely to do that. So a reward is basically like, I eat ice cream, I feel good. That's like the human equivalent of a reward. Or like, I pass this test, I feel good. That's my reward.
In machine learning, how will you know a reward
Or a penalty, whatever.
Right.
Yeah. So this is the fun part. It is a whole problem in reinforcement learning It is the reward like definition problem. I don't think that's the exact words of it, but as a reinforcement learning person, you would have to define rewards in different like situations to get the desired result. So before in supervised learning, we just had labels. Here we define reward to like give the goal that we wanted to do. So a way that like a simple reward can just be like you get you can get like 10 points when you get the cheese at the end of the maze. And you just get -1 every time step. So like you're getting worse because you're getting more hungry, I guess. So the task of the reinforcement learning person is to create the reward function. And also the agent architecture, I guess, the thing that makes the decision. So I'll go more into that later, and probably more specifically into that next workshop. So to go over the environment state, just to make it a bit more concrete, as we saw in the last picture, the previous to last picture, we have this little thing, and I'm guessing in this situation, we're moving the thing to these holes, so like to the correct holes. So that is the environment, and this is a description of the environment. So the state of an environment is different from the observation which the agent gets. And the reason for that is the state is a comprehensive description of the environment. So me as a person, I don't know every location of every chair in this three-dimensional space. I just have like an image in my head, and that's all I see, right? So that's kind of the difference between an observation and a state. The state like comprehensively defines where everything is. That might be like 10,000, 1,200, and 3,000 coordinates in the XYZ plane, but I don't know that. So that's basically the environment state. And this is like a description of the observation state, a partial, incomplete description of the environment. I know I just read that off the slide, but this is an example of it. There's no like good coordinates, it's just the image of it. So that's what the agent would get, and in a sense, you. So whenever thinking about reinforcement learning, just think of it as you, and like when you're trying to make a decision. So, yeah. A big part of the reinforcement learning problem is the agent. And one big question that pops up is, how does the agent choose his actions? This is how. It maps the observation to an action. So it could be, in this situation, as simple as being in state 0, you're dead because you died. State 1, I go this way because I'm stupid. State 2, I go this way because I'm almost stupid and almost dying. And let's say this is our goal, we get like infinite reward or something. So the policy just maps being in a certain state, or in this case, observation because you're an agent, to an action. So if I'm trying to get that chair right now, my state action pairs would be move this way whenever I'm right here, move that way whenever I'm right here. I won't move this way or that way because it's not getting closer to my goal. So that's like an example of a policy. And actually implementing it, it can be as simple as like a dictionary, where you just have a state and then it maps to an action. But the problem here would be, how do we get those actions? That is the reinforcement learning problem. So yeah. So any questions about what we got so far? I know I went through a lot of different concepts. First, we went through what the environment was, what the agent is, and the policy. So any questions about what we've seen so far? Any questions? All right, cool. So this is what a policy is. And, oh yeah, if you notice all the way to the right, it shows pi. And reinforcement learning literature, whenever you see pi, it just means policy. So yeah, and an equation is the same thing. If you see pi, it's a policy. So the next thing is value function. And this is another very core concept to reinforcement learning. And what it does is similar to policy, but a bit different. It does map something, but instead of like mapping the observation to an action, what it does is it maps the state to a value. And this is where you would kind of get the policy from. So if you have high value on this state, you probably want to go in that direction. That's kind of where you get that whole two different things here. So what a value function does, as you can see here, is right here, all at the left, it puts this area at 0, because you don't get a reward. And since you get a reward when you go over here, this part's 0 because you only get the reward when you transition. That's why right next to it is the highest value. And closer to that, it gets higher because that's where you're going to get a reward.
Why not a 1 not 0? How do you know you 6 and 0 since both is 0?
So which part?
How would you know you state 0 states since they both value at 0 not 0?
They both value at 0. Oh, so what's the difference between those two?
Yeah.
So that's just completely based on like how this problem is written, I guess. So instead of getting a reward at the state, they're getting a reward when they switch to the state. So effectively, when you're in the hole, you're basically dead. The episode ends. You're done. When you get to the goal, you get a reward of 1, and the episode ends. You're done. That's why you don't get anything else. It's just when you switch to it. So
You say 1 or 0 not 0?
So you won't get anything. It doesn't put any value here because it never actually gets there.
Okay.
Because once you go to the state, the whole thing ends. All right, go ahead.
Do you think you could maybe explain it with the example you used earlier about how the value function can progress?
Which one?
Go back.
This one?
Go back. Or in the block moving example.
This one?
Right.
Okay.
So
So
how would the value function of the policy change as it's going?
okay, so this is a bit more complicated because it's like you're moving in a, I guess, 3-dimensional space.
Yeah.
So here the states would be like probably continuous, three coordinates, right?
Or you want to use a 2-dimensional example.
Right, sure. If you use 2-dimensional example, it will be 2 coordinates. You'll probably have, I guess you can't move over here, so that would be 0. Everything around where you can't move would be 0 because you never move there. And because you're learning from trial and error, anytime you move somewhere and you don't get a reward, it will basically take that into account. So if you get a reward only when you put the thing in, it might take a lot of different trials and errors to actually have that happen and get that reward. So the whole value function thing is only based on when you get the reward, and it kind of goes backwards from that. And that is one of the problems we will look at later on. It is the credit assignment problem. So what actual movement, state, or action actually caused me to get this reward? So I don't know if I answered your question particularly, but if you get a reward with the triangle here, everything leading up to it should have a higher value. And that is just based on the way you calculate the value function, or you update it.
When you said that it didn't get it whenever it solved the action was 0 at the very end, does that mean when the moment it drops in the triangle, it is already completed? Is that why it doesn't increase anymore? Or?
So that was just particularly that example.
Okay.
So you can like describe your whole problem in a different way. You can say, when I'm in this state, I'm gonna get a reward, or when I transition to this state, I'm gonna get a reward. Because in that one, like as soon as you get to that state, it just ends. You don't go anywhere else, so it won't have any value to it. But everything leading up to it has value, because when you calculate it backwards, it like the numbers still exist. So yeah. Did I answer your question though?
I think some part of it, so maybe we can go.
Okay. So, it's fine. We can answer in the Q&A part. It- just not to disrupt anyone. Okay. Yeah, this was the next slide. Okay. The difficulty of the temporal credit assignment problem sounds very complicated. But okay. Anyways, so temporal just means time. Don't get confused. Nothing complicated. And what it's saying is that we have to assign which state or action actually caused the reward, and therefore update your value function accordingly. And I'll just walk through this example that's listed here. I remember reading it and it made sense to me, so hopefully it'll make sense to you. So you're in the environment, you're in state 0. So if you want to read ahead, you can, but I'm just going to go through it. The agent makes an action, action A, and then the environment gives a reward and a new observation, which is the new state. He gets plus 23 as his reward and moves to state 3. That's nice. I don't know what that means, but he moved to state 3 and he got a reward of 23. And then now he takes action A again, and now he gets negative 100 reward, and now he's in state 3 again. So now he's like, I don't want to go there again. And he's like, ouch, get me out of here. Now he wants to try action B, and he also gets negative 100 reward again, and he's back in state 3. So at the end, it's like, was it taking action A in state 0 that is to blame for the negative 100? Or was it choosing action A in state 0 that gave me the good immediate reward? So it's like, which thing actually gave me the reward, right? So just to bring it back, I'm in state 0, I take action A and I get a good reward. I'm in state 3, I take the same action, now I get a bad reward. Which thing caused me to get the good and bad reward? That's basically what credit assignment is. It's trying to map when I'm doing this action in this state, was that good for me? Or was it bad for me? That's the problem. And a lot of the different algorithms you'll see will try to solve this problem and another problem that we'll see next. So this is a pretty important problem. Any questions about it? Just like the problem itself. Okay, sounds good. So this is the exploration and exploitation trade-off. Okay, so I'll just go through it again. Because, yeah, I have this nice little graph here. Might as well go through it. So you're in state 0, takes action A, gets a reward of 50, and is back in state 0. Now, he's like, nice, I'll take state A again. He gets a reward of 20, and he's back in state 0. Now, he's got a lot of rewards from taking action A in state 0, so why doesn't he just keep on trying it, right? I guess in this one, I received a lot of rewards, so now let me try action B, and he gets plus 1,000. So I think he does action A a lot of times, he gets a lot of rewards, but then he tries a new action and he gets a bunch of more reward than taking action A in state 0. So now he's like, I actually regret taking action A lot of times because I could have just gotten more reward doing action B. So here the problem is, when should we stop exploring, or when should we explore, and when should we actually exploit our known information? So if I know every time I take action A, I'm going to get like 100 reward, but I never tried any other option, should I keep on exploiting what I know, which is when I take action A, I'm going to get 100 reward? Or should I explore different options to see if I'll get more reward doing those other options? So that is the exploration versus exploitation trade-off. This might seem a bit monopolistic if you hear the exploitation, but don't get confused. But yeah, so that's the exploration versus exploitation trade-off. So I'm gonna just show a real quick quiz to make it a bit, and then I'll like write up a problem and try to go through some of the math with y'all. Okay. So these are the main problems. The reason why I explain these problems here are because the algorithms we'll see try to solve this problem and use all those different components I listed out before. Okay. Let me go over textbook. So we're gonna have a live quiz like we did last time. Did we do it last time? Okay, yeah, last time. This quiz will be added to my library. Nice. So here's your quiz code. Hopefully this will be a bit engaging. So it's going to be like a bunch of questions about some of the things we covered. And since I did instructor pace, like every question, it's going to be like kind of like a Kahoot where we see the problem at the same time. And then I'll go through the question with you and explain the correct answer. Oh, okay. Yes. I don't know why you're getting points, but I think that's just how it works. All right, cool. I guess it sucks if you sign up late. So we don't really have any rewards for the quiz besides y'all's learning, so take that as you will. Yeah, so maybe I should have put a reward just to like make make the whole reinforcement learning problem like complete. You get a reward if you do good. Is everyone here? 1, 2, 3, 4, 5, 6, 7. There's 7 people. Raise your hand if you're done. All right. Are you gonna join? Yo, did you join? Oh, I started. You're good. Just like go on your phone. Yeah, you just sign in and that's it. Wait, did you put in your name? All right, you're good. All right, I'm gonna start it. Oh man, I think this was a bit different than what I expected. I guess it's not instructor paced. I'll go over the questions after anyways. There isn't that many, I think. There's only 9, so I'll go over it at the end because I thought it was like a Kahoot. Never mind. I'll raise the volume of the music. We're almost all done, so just go ahead. I'm gonna wait till everyone finishes till I get started on like explain the questions. But if you're done, you can go ahead and just wait. Okay. Still working on the problem? Sure, someone's still working on it. Wait, like look up when you're done, I guess. Anyone still working on the problems? Just raise your hand so I know. Oh, is everyone done? Okie dokie. So we have 72% class accuracy. I'll mute this. That's really good. Okay. That's about what I would expect for classes and like passing grades, so looks good. Do you want me to go over the ones most people got correct? Well, I'll just go over the ones that had incorrect. Okay. So the first question, what is an agent in reinforcement learning? So that was like the first thing I covered, which, or like the first thing once I talked about reinforcement learning. So let's see. Let me remove this part. Can we see what incorrect answer? Okay, no. I'll just go through the question and why the wrong answers are wrong and why the right one's right. So the first one is an entity that interacts with the environment and makes decisions. I think that's the correct one. Let me read the rest. The set of all possible variables and values that can represent the state of the environment. I think that's just the state. And this one, the mapping from action to potentially new states. We didn't talk about that, but that's the transition function of the environment. And third, a value function of the reinforcement learning model, which is just incorrect, because the value function. Okay, so yeah. The first think it's the correct one there. So yeah. I won't go over the one everyone got correct. So yeah. The next one was, what is a policy in reinforcement learning? So, it's a bit like, hopefully that's easier to see. I don't know if it's easier, I'll just make it in the middle. Okay, so what is a policy in reinforcement learning? I'll just go through them. A mapping between state and reward. That's not a policy. I don't know what to say besides it's not a policy. So just to remind you all what a policy is, yo, can you tell me to quiet down? Just to remind you all what a policy is it's the agent in the environment. It's they look at the state and they have to know what to do. So that is what the policy is. It is a mapping from the state to the action. That is a policy. So let's go through these again. Mapping between state to reward. It is not telling us what action to do, therefore it's not a policy. And the second one is a mapping between observation and action. Yeah, that's a policy. I should have said observation instead of state because agent doesn't know everything. And third one is a model of the environment on mappings. That is not it. A mapping of a state to its estimated value. So I think that is what a value function is, where it looks at the state and it tries to estimate the value. I think a model of the environment is on a mapping. That's just trying to learn the transition function of the environment. I'll just go over what a transition function is really quickly because I didn't cover that in the PowerPoint. So let's go back over here, I guess. So let's say we're in this environment. What a transition function is a mapping between action and actually moving to the place. Like, so if I take action, go left, I have 100% probability in this environment to move left. That is the transition function. So in some scenarios, I might not always move left. And I have let's say I have an 80% chance of moving left. That would be the transition function, where the agent doesn't know what's gonna happen when it chooses an action. It just has to kind of learn. And that's like the whole transition function learning. I'll go back to the quiz. So let's see, one incorrect here. What is a order of the experience set? So I didn't explicitly say this, but it was shown in the reinforcement learning diagram. So there is a state, the initial state you're in. You take an action, you get a reward, and then you're in your new state. So just to see. Yeah, so first you would start off in your state, so that's why this one is wrong. Because I started off over here, and then I took an action to go over here, and I got a reward, and I'm in my new state. So that's what I think the order of the experience set. And here you don't just get your reward off the start, otherwise you would have never learned the credit assignment problem. And similarly, here you get the reward, and this one you get the reward before the action, which doesn't happen because again, credit assignment, you won't know what actually caused the reward to happen. So that's why that one's kind of wrong. So number 6, what are the 2 major problems in reinforcement learning? That in mastering specific tasks, I guess that's just a description of a issue that people have with reinforcement learning. To learn a well-performing policy, it generally requires millions of samples. That's just like a side effect of the reinforcement learning algorithm. Bad at correcting specific errors. I don't even think that's completely true. Hard to make reward functions that can accurately model large environments. Wait a second. Which one is it?
It's 2.
2? Oh. Wait, to learn a well-performing. I don't think I really talked about it. It should have been like either the credit assignment problem or the exploration versus exploitation problem. I guess we missed that here. Sorry about that. But kudos for the ones who got it correct. That's what I thought the question was going to be about. Actor critic. We didn't even talk about that. Sorry about that. I guess we can just skip it because I don't want to talk about it today. All right, next one is number 8. Is blank is when a task has a natural ending or go on infinitely many steps. And blank is when tasks don't have a natural ending or could go on indefinitely. So natural ending or go on to infinitely many steps. So I think A, is this like a, you pick A question? Like,
Drag and drop.
oh, drag and drop, okay. So yeah, there's only 2 types of tasks, and that is episodic and continuing. And kind of a short description of them is episodic is like a video game. You have a level, and every time you like go through the game, either win or lose. And you get a reward when you win. And an example of a continuing task is like life, I guess. You just continue on, you continue on, you continue on. There's no like ending point, I guess, if you were immortal, obviously. But but we aren't immortal, so fortunate. But the interesting thing is a lot of the continuing tasks, they can be split up into episodic tasks. And that's what really happens in practice, because continuing tasks is kind of hard to estimate the value of. Okay, so to answer this question specifically, when a task has a natural ending or goes on finitely many steps, that would be episodic task, because like a video game. And when a task doesn't have a natural ending, this will go on indefinitely, so it would be the continuing task. Okay, so next one. Turning a car wheel is a blank continuous action space or a discrete action space. So it completely makes sense why most of y'all didn't get that, or like it was kind of a flip of a coin. It's 50-50. Turning a car wheel isn't like discrete in the sense that there isn't like 3 states. It's more like continuous in the 3D space. So that's why it's continuous. Oh wait, turning a wheel, yeah. I guess in that sense you're rotating the driving wheel. It's like a continuous angle. So that's kind of why it's continuous action space instead of like I move left, I move right. You don't really do that with the steering wheel. You have to continuously move the wheel rather than just choosing like discrete actions.
Is that always true then?
What?
Anytime you have like a joint spring, robot arms.
So those joints are in continuous action space. It actually depends on how they did it, yeah. Because sometimes they might actually just have functions that already have pre-made like left position and right position. That would have been like 30 years ago, that would have been state of the art. But right now, we've just gotten a lot more advanced in our techniques. We can use more continuous action to go directly.
So I guess what is the separation between continuous and discrete? Whatever like the steering wheel is where you stick that, like you can move that and increase like 0.1 degrees.
So here, I would think of discrete as like having predefined choices, and continuous as anything that isn't necessarily like predefined increments. So like if I'm flying a plane, I kind of have we're talking about action space. So yeah, it's just like rotating stuff, like moving your hands. That would be continuous because you're controlling your own things. But as soon as you have like an abstraction there, like where I'm moving left or right, like that's just the example. I don't know if that answers your question.
Not exactly.
So can you rephrase your question for me?
Yeah, I think in like more practical terms, I think one distinction would help is like, it seems like you can stack up a tiny amount of discrete action spaces, so they become continuous. And so where is that distinction between those two different definitions actually matter?
So in practice, this is just a label.
Yeah.
So technically speaking, it's a spectrum. And specifically when you code it up, it's just how you define it.
Okay.
That's it. It's like just how you define it. Anything can be continuous, kind of. If you do have continuous actions you're taking, you can bound those action spaces, but it's still considered continuous. But what was your question?
Even going straight, that's different. And not moving left or right.
So I think specifically where a good example of discrete was like those square boxes, because you move from one state to the next. If you have a continuous state space and an action, if you have a continuous state space, you're probably gonna have a continuous action space in the sense that how long do I move straight for, sort of thing, right? Or like, I guess in the sense of a robot, it would be like, how much should I rotate this little ankle or whatever knee thing? But yeah. So I was writing this thing down. So this is the reward function, or let me go back to the thing. I think it was expectation of reward given state in action. So that would be an estimation of the reward. Let me go back to what I was looking at, just to make sure I'm not making any errors. Yes, this is the reward function. So let me see. Sorry about this. The reason why I'm showing you the reward function is to kind of show, I don't think this is actually relevant. Sorry. I think I was trying to write down the value function. I looked at the wrong one. What time is it? Oh, wait, our time's up, so I'll just save that for next time. But so next time, I'll just kind of go over what we're going to be talking about next time for y'all. So we're going to be talking about Q learning, which is probably something, Q learning that, which is something most people use nowadays when they think about reinforcement learning. We won't go too in depth about like different algorithms. We'll just focus more on like what's used or what you can like go ahead and use. And I think we're going to go through a problem. Like here, we went through just a simple one where it was a grid world and like moving through steps. I think there, maybe we'll look at some continuous problems, but no promises. But yeah, we're gonna look at Q learning. I'm gonna show you all some snippets of code, just to show you how to go ahead and get started with that. But yeah, and I think we should talk about some algorithms too. So that's what we're gonna do. It's gonna be a follow-up reinforcement learning workshop. It's gonna be next Monday because we have our break. And I'll show y'all the last screen, which is for y'all to sign up. Do your little sign in and the feedback form. But if you have any questions, just go ahead and raise your hands and I can answer them.